handout with this t-table, the cutoff values and so on is part of that. That can be one way to present the information for you to use. We'll talk about reading that. And then do a little bit on likelihood ratio test. So the likelihood ratio test we'll talk about now, and then some next Friday after the exam. But the general way to use the likelihood function, the probability distribution function for observations, to test things about parameters, right? And so it's kind of a generalized procedure. But about exam 2, so it is Wednesday. That's when exam 2 will happen in class. For this, calculator, pen or pencil will be useful. You could have one sheet of paper, one sheet of notes, just a regular sheet of paper. You could do both sides. Right, so you should be able to write plenty of formulas on that. You can write any formula you want. You can write examples, numerical examples. You can write things that, like sentences of explanation that you might modify for your particular application. You can write things about how you do a bootstrap or bootstrap T, and anything that you might want to summarize. So you get a sheet of notes for both sides. Pretty much, so homework, the main content is going to be homework 6, right, 7, and 8. Now homework 5 really focused on Fisher information. But that's kind of an estimation technique, mostly how we were using it. And it's a little bit more involved. So we're going to start with these chapters on inference. These really are then focusing on the chapters 7 and 8, focusing on inference. And so some things that are relevant across these things for the first two there is a confidence interval. So there's a number of ways we can make confidence intervals, but then the question is, what is that confidence interval? What does that interval mean? Right? So what is a confidence interval? What does it mean in an application, which could ask you to write a sentence explaining what the interval tells you. What does the confidence level mean? So 95% or 90% or 99%. What do those different numbers mean? What implication do they have for the intervals, and why are we choosing those things? So there'll be some explanation problems like that. There'll be ones where you specifically calculate some intervals, right? So we can do a confidence interval for a mean, for mu. And if you know sigma, you use a normal distribution, so I'll put a z value here, sigma over square root of n. If we didn't know the standard deviation, we could estimate it from the data, and then we'd use a t, and degrees of freedom that you would look up would be n minus 1 less than the sample size there. Right. Again, how does the 95% impact the interval, or 90%? Confidence intervals, we'll do two-sided intervals. In some applications, you might have one-sided, but two-sided usually works fine. All right. So just that one. These intervals have a margin of error. So margin of error. Error on that. What affects margin of error? We could turn that into sample size, into one sample size calculation. Right, we could say that in setting this equal to some value, particularly in the normal case, if this is our margin of error, some value n, like plus or minus 5 pounds or something, we could calculate the sample size. We would need it for a certain level of accuracy. The z-value, such as 1.96, gets impacted by what level of confidence we want, right? And then so kind of a follow-up question to this is, when does this work well? For what type of data sets would you think that these methods would give you intervals where the coverage properties should be really believable, right? So if sample size is pretty big, central limit theorem works. If the data are not too skew, not too extreme, right? No huge outliers for a small sample size, then it should work well. Oops. So when do these methods work well? When would you expect them to work well? And by working well, also the question, what does it mean working well? So, if you're making intervals, you want the intervals to cover 95% of the time and kind of be, and kind of miss about equally low and high. You don't want it to be kind of on one side or the other. Because if it tended to miss more on one side versus the other, you could probably shift them a little bit, and it would work out. Right? So there's those questions. Another example we did is if you compare two means. So mu1 versus mu2 for our independent samples. Then we'll give x bar 1 minus x bar 2 plus or minus some t value, which has some degrees of freedom. S1 squared over n1 plus S2 squared over n2. If it's, right, we needed degrees of freedom, I could give you a value to use, or you could be conservative and use the smaller of n1, n2 minus 1. There's a big formula for calculating that from the Welch, and I won't expect you to do that necessarily. You could, but in reality, you'd go on to the computer to do it. So I'd probably say use something like, a certain number as degrees of freedom. Alternatively, you could pool the standard deviations. So if you pool them and get kind of a combined thing here, then it's that times that's 1 over n1 plus 1 over n2, the square root of that, and then we use degrees of freedom that are n1 plus n2 minus 2. If a problem is, however, is not two independent samples but matched pairs, right? Matched pairs will be like the one sample problem, right? Because we take differences because the pairs are associated with one another, and then we just use a one sample interval for the average difference based on the pairs. So, kind of connected to some of these procedures, we did mention the technical detail of something called a pivot, right? Pivot function. Right, so we had a couple, x bar minus mu, s over square root of n, for instance, was one of these, right? And so, what's the value of this? Why does, what impact does this have? How do we use, why is this special, I guess you could say. Why is this special? Why is this useful? Why is that transformation useful? Well, it ended up having a certain distribution under normal data. It ended up being a t-distribution, which we know everything about. We have a formula for the density. We can calculate endpoints, cut points, probabilities under it. We don't need to estimate any parameters for a t-distribution. We need to know degrees of freedom, right? But there was some use, right? And we use that to derive a confidence interval. So how do you turn this into a confidence interval? We also did confidence intervals for proportions, right? Those are formulas that could, so for one proportion, we had p hat plus or minus a normal value. And we estimated standard error as p hat 1 minus p hat over n. Or if we did difference of two proportions, there was the difference of proportions to get our estimated point, plus or minus a standard error, and it was the sum of those two standard errors. It's rather the sum of the two variances. And the square root of all that gives us an interval. So that might be another formula. Right? There were a few modifications to that in there to maybe make the intervals work out a little bit better, but for our purposes, it will be okay to just use the simple formulas in terms of that. Right? This one, for instance, there was one condition to check that it seemed like it was, well, a couple. It really seems like a binomial experiment. Like you have one sample, the proportion should be the same for everybody in the sample, and they're really independent, right? It makes sense if this is a binomial, so-called binomial experiment, binomial Bernoulli trial. We also wanted the sample size to be not too small, you know, something like this. Right? And so our question is, why is this important? Why do we need a sample size that's not too small for this interval to work out okay for us? And again, what does it mean to work out okay? Right? We want intervals to cover, so we're approximating the sampling distribution by a normal. Right? Approximating the sampling distribution by a normal. So you need a certain sample size and not too clustered towards 0 or 1. 0 or n for the number of cases for it to actually work out. Right. Another way of writing this number here, this is x. That would be the number of successes, whereas this one would be n minus x, the number of failures. So you want enough successes and failures that you're not really close to the boundary, because a normal curve doesn't get smushed on one side, you know, very well. It has to have its tails go out to make it look realistic. Right. The other way we did confidence intervals was a bootstrap T interval. And let's think about, we can focus on just a single mean. We talked about we could do bootstrap T for a bunch of different cases. Let's just think about one mean, right? And in this case, we bootstrapped a statistic. We bootstrapped the T statistic. We took bootstrap samples and compared the sample value in our bootstrap mean sample to the original sample, and then divided it by this. Right? And so this was used, so simulation is used in place of the t n minus 1 theory distribution. Right? So what you could be asked to do, is if we're interested in the mean, I'd probably have you do one of the regular formulas, like a t interval with the standard formula. But then say, well, how would you implement this to get bootstrap t cutoffs instead of the t distribution cutoffs, right? So you could describe a bootstrap algorithm to do it, right? And then given output, from a bootstrap t simulation, report something like a confidence interval, right, for the mean. Right? So that was, it was with x bar minus the 975 point of this t star distribution up to x bar minus the lower one, 0.025, which would be negative. So it's like adding something there, right? S over the square root of n. And this is the square root of n. So if I gave you x bar, s, and n, you'd probably have those values from just doing the ordinary procedure, right? And then if I showed a histogram of the RT stars, you could pick out a couple points, and or maybe I would give you some cutoff values, right? And you could take that and then make an interval for it. Right? When would you like to do this test? Right? Why would you like to do the t simulation versus the other? Yeah.
When the distribution doesn't follow the assumptions for the t distribution.
Right. So if the data are skewed, small sample, so that the sampling distribution of x bar looks a little bit skewed, then this one interval is going to be shifted a little bit one way or the other. So you could give a rationale for contrasting that. So that would be kind of it for the confidence interval. So, problem on proportions, a problem on means, some interpretation, comments on things. On this chart, right? So depending on degrees of freedom, you need some cutoff values, right, for deciding things, and that's what this thing has. Right? This is what books typically have done in the past. One thing to note is that at the very bottom is infinity, so infinite degrees of freedom is the normal, right? So degrees of freedom, infinity, this is normal. Right? And the things across the top are the percentiles, right? So for 95% confidence interval, right, you need the 975 percentile, because you leave 5% left over, 2.5% above, 2.5% below. And so if you go all the way down here under 0.975, you get our value of 1.96. Right? So that's a familiar value for 95% confidence interval for normal. Right? But if we had, say, one sample problem in n equals 16, we would use degrees of freedom of 15, right, across there. And that value in there is what you should replace. Instead of 1.96, should be the slightly larger value. Right? So if we had 16, right, what are we going to do? We're going to look up the 15 row. Yeah, 2.131. Is that 2.131? So you would look up that as a multiplier, and that compensates for the fact that you're using an estimated standard deviation. Right? Which column would you look at for a 90% confidence interval?
0.95. It's 5%.
5%? Yep. So 90%, 10% left over, so 5% on each side. The 5% above mean 95% below. Right, so 1.645 for a normal, or this, if it was t, 1.753. How about a 99%? confidence interval, right? So 0.950. Right? You don't want to look up just 0.99 because you got to get 0.5% on each side, so 0.995. That's almost at the end there, right? So 2.576 for a normal, or if it's that particular t, 2.947, bless you. Right. So I can give you a copy of this table along with that, and then you can look up your cutoff values and compare, you know, as you get more confidence, it gets wider, and things like that. So. And on Monday, we'll do some review. I'll get an electronic version of this, and we can look things up and double check, you know, practice for that. But, you know, so, you know, if you read the subset there of the source, you know, Fisher and Yates statistical tables for biological research, I think those were originally published in the 1930s, right? So how did they do it with, you know, without computers? Maybe it was 1960s or something. But, you know, basically it's hand crank approximations to integrals and things like that. So the early biology, it was quite something to publish a table of numbers to 3 decimal places and things like that. But now we just pop it on the computer, right? So early achievements. That's using that table. Chapter 8 does some things with hypothesis testing. So maybe a couple questions on confidence intervals and interpretation, a question or two on hypothesis tests, right? That we'll focus on 8.1, 8.2, and 8.4 of the book. We can do a hypothesis test about mu. Bless you. Is mu equal to a certain value or not? Right? And we calculate a t statistic for that, x bar minus mu sub 0, you know, s over the square root of n. Right? We could do a hypothesis test about the proportion. You know, p equals p sub 0, or the alternative that is not equal to that. And this one we calculated a z value. We standardized under the null, tells us to use this one to fill in this standard error, this variance here. You know, another way we did the test is there was a bootstrap t-test, which is the bootstrap procedure is going to be very similar. This thing is distributed as t n minus 1 up here, but if we don't think that the sampling distribution is quite normal, we can simulate that. So the bootstrap t-test, make a bootstrap sample, you calculate new t values, and then you compare your actual t statistic to that reference distribution. Right? But we can go over that as an example. So describe procedure. And you know, how does it go? Write out a few steps of how you would calculate those things. And given some output, I'll give you a histogram of t star values. And you have your own t value. Doesn't seem to change very much, right? So the recently we just introduced this idea that type 1 and type 2 errors, and sometimes you make an error by rejecting a null hypothesis that's true, or you don't reject, and you should. And those, so some interpretation of those, not necessarily getting numerical things, but what does it mean? Because that kind of flavors the intuition. And finally, this power calculation. Right? We could do something like that, right? And the one thing is we'll do it about a mean. So just like we did in the, you could use normal for that, just like we did in the, but some of the power concepts are, you know, if you have larger sample size, why do you get more power? Right? And something like that. So there's really, just by focusing on that part, not every chapter, and leaving out the likelihood, or the Fisher information, there's still quite a lot. There's a number of formulas, a number of explanations, and that's, you can have a sheet of paper to write some things down. So I think looking over homework 6, 7, and 8, and those chapters, and the notes that we did in class is the key to studying for that. In addition to a flood, my computer rebooted in the middle of preparing some documents. So I have I'm getting some problems ready that would be study practice problems, but that caused me a little delay this morning once I got into campus. So but those will get ready. I intend to post them with some solutions before the end of the day, or the solutions I might post to it tomorrow, sometime tomorrow, but you would have them. We can go over those Monday. That will illustrate particularly the numerical calculations of things, a little bit of the interpretation. That would be the exam. So kind of a time to review. The first exam was more about estimation methods, method of moments, maximum likelihood, unbiased tests, things like that. What is standard error and sampling distributions. This one is focusing on these methods of making confidence intervals, doing some hypothesis tests. So this does restrict it. I am restricting it, so you don't necessarily have to do hypothesis tests about 2 means or 2 proportions. So that reduces it a little bit in terms of the focus. But any questions about that? So we've done a few methods, but really these are critical methods because of how much they're used. And they illustrate the underlying ideas that then translate into much more complex problems. Right? So the new topic, right, this will not be on the exam, but we would take it up again and do a little bit more with it on next Friday, and then it would be on the homework after that. So no homework due next week. It would be due the week after that. The new topic, and this is in 8.6, likelihood ratio test. Okay. So some of the confidence intervals and hypothesis tests we've been looking at, bootstrap is kind of a general idea that works across a whole variety of things. But the specific methods like the t-test or the test for proportions have dealt with those distributions. But what if you have Poisson? What if you have exponential? What if you have something that's much stranger, like a mixture or something, right? And you want to test assumptions about those. And those hypotheses correspond to key biological problems, so you want to have a parameter or something corresponding to that. How do you do that? Well, likelihood ratio test is one way that you can test some of those things. Right? So we go back to looking at a probability density function, or a probability mass function if it's discrete. And so we write that as f of x for a parameter theta. And then our question really is, what is theta? That's our inferential question. Right? And we're going to approach that as a hypothesis test. We're going to get data, x1, x2, xn, and we're going to assume that they're independent from this distribution, so that the joint distribution of all the data together, all the values we would see, dependent on theta, becomes a product of all the individual densities. The book writes the semicolon here. I sometimes write a straight line there to mean that's something as part of the model, and the data there are x. Viewing this thing, though, as fixed data points, and theta is our unknown parameter, we call this the likelihood for theta. Right? So that should tell us, we use maximum likelihood to find the best theta for our data. We maximize that thing to find the theta most consistent and made our data most likely. Right? Such that if you put in theta hat, then this thing was a joint density had as great a height as possible. Right? So, but in hypothesis testing, we're going to have values that we think are plausible for theta, right? Well, we could look at what the likelihood score is here, given those values. Right? And so, initial way to do it is to think about a null hypothesis versus some other value. Right? The starting point. These are called simple hypotheses. Right? Because there's just one value there. We have these two things, and how do we want to compare them? Right? Well, for each of those values of theta in our data set, we can calculate the likelihood value. Right? And so the likelihood ratio, I'm going to call it a capital lambda, the likelihood ratio statistic is going to be the likelihood at theta 0, and just to remind us that we have a bunch of data points there, divided by the likelihood at theta A. That's how it's usually written. So we're going to see the likelihood value there. You could take the differences, but we're going to take the ratios. There's a reason we take the ratios in terms of some statistical theory later on, and a limit, right? Right. But the likelihood will be big if theta 0 is good, right? Or this one will be big if theta A is better, right? So we end up rejecting the null hypothesis for small values of this likelihood ratio. Right? So we want to reject lambda for small, reject H0, not lambda, for small values of lambda. Right? So you could say reject H0 for lambda less than some cutoff C. And so we have to determine what C would be, right? C, the choice of C, will correspond to our alpha significance level. Right? So if you choose smaller things, right, then it becomes harder to reject, right? And this has to be a lot better, a lot bigger in the denominator for very small values of C. Right? More moderate values of C, it only has to be a little bit smaller. Right? So smaller C means smaller significance level. And sometimes we can figure out exactly what that would be through a little bit of work and transformation. And we can figure out a certain probability, but we'll see that in an example. Right? One result, extremely important result, is called the Neyman-Pearson lemma, named after Jerzy Neyman and Egon Pearson in the 1930s. Right? That any other test with an alpha level chosen less than some chosen alpha, this is alpha, right? Has to have less power than the likelihood ratio test. Right? So for any fixed level alpha, for these simple hypotheses, the likelihood ratio test minimizes the type of error. So the likelihood ratio ends up being the best test at a certain alpha level. Right? So it's a big result. So how should you test? You could come up with all these different statistics, all the different things to look at. But if you focus on the likelihood, in simple hypotheses, you get the most power at a certain error rate. Right? So that's great. So the Neyman-Pearson lemma. So one way of summarizing that for a fixed alpha, the likelihood ratio test with cutoff C corresponding to significance level or type 1 error rate alpha. This minimizes type 2 error. So if you choose another one that has an error rate alpha or even a smaller error rate, smaller error rates usually, you decrease type 1 error, you usually increase type 2. You trade off, right? So but if you get any other ones that have the same error rate, it's going to have at least that bigger type 2 error, so likelihood ratio tests should have better performance. Right? And that'd be a way to do it. So how do we implement this kind of in practice? What do we tell in practice? Right? So there's a couple of examples in the book that you could work with. This does it for an exponential distribution. Example 8.21 does it for a Bernoulli, so Bernoulli binomial type of situation. So you can look at those. Example 8.22 does it something with a Cauchy distribution. And Cauchys are weird, right? Because Cauchys don't have means. They're T's with 1 degree of freedom. And so they have really heavy tail. They don't even have means or variances and things like that. So it's a bizarre distribution. So it does, the results there I think are correct as they state them, but it's a little bit hard to think about what it means. The Cauchy is so unusual that it's a little bit counterintuitive in terms of the result, right? But so these two would be great to get because they're consistent with what you would think would happen. The Cauchy's interesting for mathematical statistics, but it's a little bit more of a
Edge case?
Yeah, edge case. It is an edge case. Yeah. So let's say that our data instead are Poisson. So we'll get a little contrast to the examples that are there. Right? Poisson random variable with lambda has probability lambda to the x e to negative lambda over x factorial. So if we have data that are a bunch of observations, the probability is that of all our data, writing in a little vector shorthand with x1, x2, xn, all of those, is going to be the product of all these things. There's a lambda to the xi, e to negative lambda, and there's an xi factorial. Right? And as we combine these things, there's a lambda to the sum of xi, e to the negative lambda n. And then there's this product of the xi factorial. And so that's the joint distribution. And if we want to compare two lambdas, lambda 0, lambda, rate 1, rate 2, lambda 0, lambda a, just putting in our data values here in the sum of the x's, putting lambda 0 here and lambda 0 here would be the likelihood evaluated at a particular point. In likelihood theory, the part of the data, how it interacts with the parameter, gives you something called a sufficient statistic. And so in this case, we haven't really emphasized that terminology, but the sum of xi is called a sufficient statistic. For lambda. So it's the sum where you need to know to compute the likelihood function, or up to a constant, or the log likelihood. So this is the important summary, the sum of the xi's you need. Right? So let's look at our likelihood ratio under two simple hypotheses. Right? So we have the first one, lambda equals some lambda 0. There's an alternative that lambda does not equal. Oh, we'll do it simple. Right? Lambda a, some alternative value. Then the likelihood ratio test statistic, which I call big lambda, right, is the likelihood evaluated at L0 over the likelihood evaluated at LA. And so this one is L0 to the lambda 0 to the sum of the xi's, and there's e to the negative n lambda 0. There is the product of all those xi factorials there, but it's in both the densities, so it'll cancel once you take a ratio. And then lambda a, the sum of the xi's, and e to the negative lambda a. And for the time being, let's assume that lambda a is the bigger number. So this thing can be small. It can be less than 1, right, if the data are, in fact, small. Right? If the data are small, then the lambda 0 that's smaller is going to be better, be more consistent with it. Right? But if the data are big, if you have a lot of observations, they add up to a lot, then lambda, the rate, should be bigger. Right? And so this. Right? So we're going to reject the null hypothesis if lambda is less than c. So if this thing is less than c, I don't really want to write that again. Let's write this, let's simplify this a little bit though. Lambda 0 over lambda a times the sum of the xi's. And this is e to the negative n, and there's a lambda 0 minus lambda a. So combining these two terms and combining those two terms, you see how this is contrasting the lambdas. Now we want that thing less than c. So we can manipulate this now to try and find out what condition this says in terms of the sum of the x's. Or we can isolate the sum of the x's by manipulating that, right? So you can take logs of both sides, right? So if you do that, what do you get? Take the log of both sides, and right, you get the sum of the xi, the log of this thing, log of lambda 0 over lambda a. And you could change that a little bit. And there's n times lambda 0 minus lambda 1 is less than log of c. That's the condition. And then you're going to add this thing over to this side. You add it to both sides, right? So it cancels over here and appears over here. And then we're going to divide by this thing. So the sum of the xi, now log of c, right, adding something over here, that's fine, minus, and then dividing by log, I forgot to write the ratio here, lambda 0, lambda a, sorry, that's small. Just write the plus over, it's easier to read. And then we're going to divide by the log of this, right? Now here's a little wrinkle. If lambda a is bigger, this is less than 1, and we're dividing by a negative number. Right? When you divide by a negative number, I get that flips. Right? So here's this log of lambda 0. It's also can be written as the difference of the logs. Right. So this says reject the null hypothesis when the sum of xi's are big enough. So you should choose the bigger lambda rate if the xi's are bigger. So that makes some sense. But you do have to remember that dividing by that thing is negative. Right, so let me make that right. Right, this is negative. And so emphasize that changes that flips that around. Right? And we can use a little statistical theory to figure out what our alpha levels would be and what type of cutoffs we should use. Right? So now we can phrase all of our cutoffs in terms of the sum of the xi's. Right? Likelihood ratio test is equivalent to making a decision based on the sum of the xi's. Right? You get enough rates, you have to choose the bigger one.
So you just swap log of c.
Right.
Right, 'cause where's the log of c?
Log of c. Oh wait, so log. Oh yeah, I'm sorry. That's a mistake. It was just log of C.
Oh, okay.
Yeah. Sorry about that, I got confused. Yeah, it was log of C, and then I added this thing to both sides, and then I divided.
Okay.
Yeah, so I forgot to put C, and then I got confused about what I should put in there. So Poissons, independent Poissons, have a nice property. If you add Poissons together, you get another Poisson. So if xi are independent Poisson lambda random variables, right, then the sum of xi, I going from 1 to n, is also Poisson, but now with rate in lambda. Right? And so we're going to reject h0 at lambda equals lambda 0 if the sum of the xi is greater than some number. Let's call it c prime. Right? C prime is the complicated thing that we did. We just know that it has to be big. Let's make it greater than equal just to make it simple, right? It's discrete, so is it at that integer or one more? You can figure that out, right? If h0 is true, we can calculate alpha. Alpha equals the probability that we reject h0. That's its meaning, right? That's the significance level, that's a type 1 error rate. If the null hypothesis is true, but we reject, that's a type 1 error, and this is our probability. So it turns into the probability that the sum of the xi is greater than or equal to this number, right? And so under a Poisson probability, that's a sum of x going from c prime up to infinity, the probability that some number equals x, where x is distributed as a Poisson random variable with n times lambda 0 as its expected count. This is a capital X, right? And it's a little lowercase x number. Right? Right. So we can calculate the probability that all the possibilities that would lead us to reject, if the null hypothesis is true, that's the chance we make this error. We would probably not try to add from 0 to infinity. We would probably take 1 minus that we do not reject, right? But that's the alpha level, right? So our likelihood ratio, where the alternative is bigger, tells us to reject if we get big means, right? And then we can choose a cutoff based on this probability distribution to tell us where exactly is big enough. Right? So let's do a numerical example, right? So let's say that the number 100-year floods, and this is the example on Wikipedia when you search up Poisson. I didn't choose it because of the rain, but it's kind of funny, right? Coincidence, yes. And that we sample 10 places. It might be in this, 10 spaces that are spread apart. 2 places really close together probably have the same results, but if they're spread apart, they're different river systems, different watersheds, and so on, then maybe they're different. And we count the at each place, we count the number of 100-year floods during 10 years. Each xi could be modeled as a Poisson random variable with some rate.
What's a 100-year flood?
Well, so 100-year flood is, it's confusing, right, in weather and things. So there are floods that are supposed to a level that's only supposed to be reached one every 100 years.
Oh, okay.
Right. But it doesn't really have that meaning, as I understand it, because 100-year, 500-year floods happen fairly regularly somewhere, right? If there's thousands of places across the country, you get it more often. But, so it's just some big flood level, right? And say that we would expect this to have a Poisson distribution. And let's contrast two values. A null hypothesis says it's 1, and an alternative says it's 1.5. Maybe the flood rate of extreme events has increased. Maybe climate change, maybe some other calibration measurement in the past that said the 100-year floods was an error. So for whatever reason, there could be different rates. These two probabilities imply different likely outcomes. So the values of x you're likely to see 0, 1, 2 from these different parameters. The parameters imply things. Right? ... If lambda is 1, there's a 36.8% chance of having none. No super big floods in 10 years. The probability of 1 is the same because of the probabilities. I'll draw a line here to keep things straight. It's an 18% of 2, 6% of 3, 1.5% of 4, 0.3% of 5, and then it goes smaller after that, etc. It would go on forever, but with increasingly small probabilities. If it's 1.5, however, there's a 22% chance of 0, 33.5% of 1, a 25% of 2, a 12% of 3, and then 0.047, 0.014, 0.0035, etc. Right? So, kind of at this tipping point here, the larger rate is less likely to have zeros and ones, and more likely to have bigger numbers. So let's say we have a data set where our 10 numbers are 0, 4, 0, 0, 1, 1, 2, 1, 1, and 3. Right? We have 10 different locations, and these are the number of times 100 years of floods have hit those locations. Right? So the sum of the xi's is 5, 6, 7, 8, 9, 10, 13. Right? Lambda hat would be, in this case, estimated as 1.3. So it's bigger than 1. But is it big enough to actually reject 1 in favor of 1.5? Right? If this number had been 27 or something like that, then it would have been okay. That's probably right. And so the question, so then to do the likelihood ratio test, we're going to calculate this likelihood ratio. Right? So when lambda is 1, and you raise it to the power of 13, e to negative 10, right? 10 times 1 is 10. That's n times lambda, goes up there. Right? In the denominator, it's 1.5 to the 13th, and then e to the negative 15. Because down here, if the alternative is 15 times, no, it's 10 times 1.5, and so that's 15, and that's m times the alternative one there. Okay? So that's the likelihood ratio. That value ends up being negative 0.0271. And we have to decide, should we reject or not? Is that low enough? It's often hard to tell, what this scale means. Is that a real small value or things like that? So let's suppose reject H0 if lambda is less than 0, if it's just negative. Right? Why is it? Oh, this is a log. Right, sorry. I take a log, right, of this, right? That's why it's negative. I was wondering, why is this negative? And so it's the log of all this, right? But because the log is less than 0, that means the ratio is less than 1. So it means that the 1.5 is a more likely value than 1. What is the implied error rate? What's the implied alpha level? The log likelihood ratio is less than 0. Well, you can figure out that this thing implies that the sum of the xi is greater than or equal to 13. How would you do that? If you put a value of, well, it's a little, let's see if I have it clearly now. Here. So alpha ends up being 0.136, right? So if it's greater than 13, if we're greater than this, what's the probability that the sum of the xi's is greater than or equal to 13 if the rate for this is our 10 observations times a rate of 1, a rate of 10. Right? What's the probability that a Poisson gets you more than 13 observations if the rate is really 10? Right? And so in R, there's probabilities of Poisson. So the probabilities you're less than or equal to 12 when lambda is 10 is about 79%. Right? So the chance that you're bigger than that, bigger than 12, means 13 and above, right, is 1 minus that. That was about 20.21. Right? So if you reject, my note's a little confusing. So let's drop this out of there. Right? That doesn't seem relevant. This is about 0.21. Right? Which would suggest that our alpha level for that test, just splitting it at 0, or the ratio has to be, if it's less than 1, we reject. Our alpha level is going to be 0.21. That's not too strict. Right? What sum value should we use so that we actually do get an alpha level that's more realistic? Right? How big should the sum of xi be so that our alpha type 1 error rate is about 0.05? Well, we're going to look at the null distribution, right, which says that the sum of the xi's should be Poisson with rate of 10 times 1, 10 observations, 1 each, which is, of course, just 10. Right? So we look at that Poisson and see what are the errors. So we can look at the density for a Poisson. Well, there's quantiles for a Poisson, just like there's quantiles for a normal or quantiles for a T. So we want a point that has only 5% above. So if we go past that, it's less than 5%. So 0.95, 95th percentile, if we're above that, we can reject. And then lambda is value of 10. And it says 15. So what does that mean? Exactly, 1 minus the Poisson, if we reject the chance that we're at 15 or above, and equals 10, so 0.048. So if we want to test that at a 5% significance level, for this case, the likelihood ratio test, say, reject if the sum is over 15.
Why'd you use 12 instead of 13 before?
This one, so let's see what it was back over here. So we had 3.
13.
So this one was, yeah, at 13. So if we rejected with a sum greater than or equal to 15, what's the probability we're greater than or equal to 15?
13.
Right, 13, yeah. What's the greater than or equal to 13? What's the probability of that? So we can calculate the probability we're less than things.
So we're calculating
Like
probably they were less.
12 or less. So 1 minus that is the opposite.
Okay.
Right. So really, yeah, so this other calculation is, this one says, right, reject if the sum of xi is greater than or equal to 15. Is that what it's saying here? And then what do I get when I do this calculation? This is the probability that's greater than 15, right? So it's really, you have to be careful with these things, right? But to get that really, if it's greater than 15, then the alpha level is 0.0 or something, right? So this one, this is 15 or less. And so 1 minus that is greater than 15. If we reject it for 15 or above, this thing would become 14. And it's about 0.083. So if we allow 15 to cause rejection, we were a little bit bigger. So as we push that sum of xi's out there, it becomes harder and harder. And the probabilities under that distribution become smaller. So this is kind of an introduction to this likelihood ratio testing. Okay. And so we have a model for the data and 2 hypotheses about the parameters. Right? We can calculate this ratio, and then sometimes we can turn it into something about the distribution, and in fact figure out probabilities of errors. And we'll look at another example in a week. Right, the immediate task is reviewing for the exam and going over practice problems with pretty close. And if you haven't turned in the homework, there's a pile up here for this new one. I'll try to get that back to you. Worked out.
No, I did the homework last night. First 3 problems. I went to do it today for my stuff. I was having a little problem.
Oh, no.
What's up?
Thank you.
Yep, I'm gonna reach in.
I'll figure it out sometime.
You too?
Do you have a stapler?
I have one in my office, so I can take it.
Keep it.
Yeah. Weird weather last night. It was really warm.
Oh yeah, it was insane. The flooding and stuff going down in Burlington was unbelievable.
Were you down in Burlington for the?
Yeah, I was down at UVM and then went to the bars.
Yeah.
And look at this video of when we were in transition to the bars. It's insane.